yesterday. Yesterday we had a look at the spectrum of so far unconfirmed theories that are highly influential in current fundamental physics. And there is one last theory that plays a crucial role here, of course, which is the complex of theories about quantum gravity. And since Karen has talked about quantum gravity yesterday, I can be fairly brief here. I just want to lay out a general line of reasoning why this is important, and then say a few words about string theory specifically. So this connects back to the early introduction yesterday, where we had some thoughts about, or I expressed some thoughts about unification. And one way of viewing theories of quantum gravity is in terms of the last step of unification in fundamental physics. The story goes that there is, on the one hand, the standard model of particle physics, so the theory about those interactions that play a role in understanding microphysics today, and on the other hand, general relativity. And the problem is that those two fundamental theories are inconsistent with each other. They are based on inconsistent principles at the face of it. In quantum mechanics, there is a rigid space-time background, while in general relativity, the curvature of space-time is directly related to matter and radiation. So there are problems to understand how one can bring those two together, and that is important because there are regimes where both forces are relevant. And those regimes are either at the very early stages of the universe, where the energy density is so high that the gravitational coupling becomes of comparable strength to the microphysical couplings, and also in the interior of black holes, where similar situations arise. So the idea is, and we have discussed a little bit, or Karen has discussed a little bit, alternatives or these questions. The idea is that there is a fairly widespread understanding that we therefore need a theory of quantum gravity that can jointly describe gravitation and nuclear forces. And if we now remember back yesterday's discussion about unification, of course, this is a paradigm case of the role unification plays in physics, where there are two theories that can characterize different domains, but there is in between a domain that cannot be characterized by either of them, because both of the first forces that are described in the individual domains become relevant. So in that domain, it is clear that something new has to be done. If that's a fully unified theory, that means that this theory will also increase the precision of what's going on either side in the initial domains. Okay, so yes.
May I ask a quick question before you go on?
Sure.
So the very last item on the last
Yeah.
slide. So general relativity works, where nuclear interactions are not relevant. I mean, what do you think about the calculations that were done in the 30s and 40s, working out the neutron star structure, where they did in fact, take account of what they knew about internucleon forces, and they were using general relativist models?
I mean, of course, there are ways to some extent to characterize situation where both sides play a role. There are semi-classical descriptions, and so it's not the case that you can't do anything without a full theory or without a theory of quantum gravity at all. But it is clear that once you get to the core of the high energy regime, those approaches don't work.
Thank you.
Yeah. All right. So string theory is also, like all the other theories we have discussed, is a theory that is by now more than half a century old, and it aims at providing such a fully unified theory of gravity and of all interactions. It was developed in the late 1960s, initially as a theory about strong interaction, and interestingly, one problem they faced that they soon understood that this theory implies a graviton. So it has an excitation mode that just doesn't fit strong interaction. Then there were other issues with that initial context of thinking about string theory. In particular, what then came along is a better understanding of quantum field theory, gauge field theory, and the understanding that gauge field theory actually could explain confinement. Therefore, in the early 70s, it became clear that string theory is not the favored perspective or approach towards strong interaction. However, then there was the proposal that if that doesn't work, it's still interesting that string theory implies a graviton. Therefore, a string theory might actually be a candidate for a theory of all interactions. And that's in 1974, the starting point of string theory as a universal theory. Now, the basic idea of string theory is to replace the point-like particles by very small extended objects, the strings. And that looks promising from a perturbative perspective because it may solve one core problem of quantum gravity, which are, as we heard yesterday from Karen already, which are the uncontrollable infinities that arise in calculations once gravity is included. Initially, string theory in that context was only one proposal. It turned out that other proposals did not work, or it was plausible to think that they wouldn't work. So string theory then became a leading proposal on that issue. So the understanding, once you have introduced these extended objects, these strings, is that all quantum numbers, spin, charge, etc., can be understood in terms of oscillation modes and other spatial characteristics of the string. And what happens once one tries to make this approach consistent is that one understands that consistent string theory implies a wide range of fairly surprising and characteristics that don't seem to have any close connection to the world we observe. For example, one needs to introduce extra spatial dimensions. One needs to have, in the case of the superstring, a 10-dimensional background space on which these strings can propagate. The additional dimensions then, of course, must be treated in a way that can explain why we don't observe it, and the standard procedure is to assume that they are compactified with a very small radius. So they run back into itself after a very small distance, roughly the distance of the order of the string length itself. Then further investigation leads to additional structural aspects that arise. Higher dimensional objects, the so-called brains, enter the picture once one goes beyond the perturbative description of string theory. Yes?
What was the last line? It was blocked.
All right. Can I? So higher dimensional object must be introduced at a non-perturbative level. All right. So now if we compare the perspective on string theory or the current understanding of string theory to, for example, quantum field theory, one understands that string theory is in a fairly peculiar state, let's say. If we think about quantum field theory, we start with a full representation of the theory. So the theory or a model of a gauge field theoretical model can be spelled out in terms of specifying the Lagrangian. So you introduce all the fields, you introduce the coupling structure and so on. Then it is important in this context to introduce perturbation theory because you want to extract quantitative predictions. And so perturbation theory is a method, if the theory is weakly coupled, to extract such predictions to quite high accuracy. In string theory, the situation is different because there is no full formulation of the theory that is known. So the theory started at the perturbative level by changing the understanding of the perturbative level of a theory. So one introduces those extended objects rather than point-like objects and formulates the scattering amplitudes at the perturbative level, including those, or using those extended objects. So, therefore, it is not clear up to this point still how the full theory is actually related to what one knows. Since there is no full specification of the theory, various things might in principle happen on the way towards a full understanding. And there is a canonical understanding that suggests that actually what is known about the theory at this point, and this is this perturbative entry point plus the dualities we will be talking about in a moment, that this in an unequivocal way specifies the full theory. So the idea is that everything that needs to be said to point at a specific theory has been said already, but it's not fully understood how the things play out. So on that understanding, string theory is a specific theory, and the question, the problem just is to understand what the implications of the stated definitions of string theory or the characterizations of string theory are. It is not entirely clear that this is the case, and there are some suggestions that point in a slightly different direction. Verlinde is one example of that, right? He thinks that that string theory is not so to say, it doesn't cover the full range of possible dynamics, but just specifies the specific endpoints, the symmetric endpoints in a larger spectrum, which would mean that the full theory has broader characteristics, and it's not that clear then how to think about the full theory. So not even this is entirely clear, even though there is, let's say, a prevalent understanding that string theory is fully specified by what is known. Now, what then happened in the mid-1990s was that a powerful tool for reaching out beyond the perturbative regime was identified, and that's string dualities. Dualities, of course. Okay. So maybe I need to. Something here. Is there something? I don't know. Okay, now I think it works. Yeah?
Yeah.
Yes.
Yes.
Yes. So it was understood that different formulations, the different types of string theory, as they are called, are related by duality relations, meaning that one set of parameter values of a type of string theory that sits in the perturbative regime, so the string coupling, for example, is small, or the extra dimension is big, let's say, is related, or small, whatever the perspective would be, is related to a dual and empirical equivalent formulation that is based on a different type of string theory. This empirical equivalence then allows to reach beyond the perturbative regime, because the duality transformation leads from a perturbative regime of the one theory into a non-perturbative regime, or vice versa. So you can move into a perturbative regime based on those duality relations. And the two crucial theories that then connect all types of string theory that can be built in 4 dimensions or in 10 dimensions is T-duality that relates winding modes of a string on a compact dimension to transversal momenta of that string on a compact dimension of inverted radius, and does also some other stuff. And the second important duality is S-duality that relates different string theories. One string theory to a string theory with inverse string coupling. And this web of dualities then also leads towards or points at what is called M-theory, that in order to complete this web of dualities. Then a few years later, ADS-CFT correspondence was discovered, a different type of duality that relates a string theory on ADS space to a pure gauge theory, conformal gauge theory, at the boundary of that space, so in a space of spatial dimension that is reduced by 1 dimension. So together with the perturbative entry point based on dualities, one has a considerable degree of understanding of the theory, but one doesn't by no means have a full understanding on that basis. So it's not clear how the fundamental dynamics in the non-perturbative regime works, and how for example, the selection of ground, or the generation of ground states from first principles of the theory can be understood. So yes, so that's all I want to say at this point about the theory. Let me ask you whether there are any specific questions at that point, just about the theory itself. So let's have a look then at the support for string theory. First, of course, one needs to point out or emphasize that string theory does imply the two theories that are empirically well confirmed and that it is set out to join. So first, it implies that the low energy particle theories must be gauge field theories. So if one looks at a theory and asks, okay, so what is the low energy limit? That low energy limit will be gauge field theories. A second, it implies that an effective theory of that theory is general relativity. So string theory implies the existence of gravity and the validity of Einstein equations in some approximation for consistency reasons. String theory also seems incompatible with a number of possible low-energy scenarios. So those are not entirely ruled out because the situation is not sufficiently understood, but there is an entirely field of research, or by now one may say two fields of research in string theory that focus on understanding low-energy implications of string theory. So there is, on the one hand, what is the string phenomenology approach, which is a traditional approach that has been carried out for several decades already. And then there is the more recent approach of swampland conjectures, as it is called. And what they suggest is that there could have happened. So first, what string phenomenology emphasizes is there could be a world, in principle, one could imagine a world that does not look nice from a string theory perspective. For example, higher representations of a gauge group would be difficult to reconcile. One has to say, however, at that point, that there are also aspects of string theory that seem to be not well tuned towards what we think we observe. So, for example, it is difficult to extract inflationary scenarios from a string theoretical starting point. So it seems that inflation in a sense looks disfavored by string theory, actually. And another point is that it seems to be there is a swampland conjecture that states that de Sitter space cannot be generated in a string theoretical framework. But of course, since we observe accelerating expansion, the cosmological constant that corresponds to it would suggest that we move towards the de Sitter phase. So something has to be tuned there or corrected there in order to bring those two together. So these implications from string phenomenology and swampland are not consistently in favor of string theory. One can say it's a mixed record. However, having said that, those implications are not fully understood, neither the positive nor the negative one. So it's not clear how strong the implications are. If one looks at the core posits of string theory, which are extendedness of the string and extra dimensions, there is no empirical confirmation of these posits, and it is not awfully probable that there will be any in the foreseeable future. There are some scenarios that move those closer to empirical access, but it's not clear how realistic those are. There are also no specific quantitative characteristics of low-energy physics that can be predicted at this point, which has to do with two things. On the one hand, the lack of understanding of the fundamental structure of the theory, and on the other hand, the huge set of ground states possible that can possibly be assumed in a string theoretical basis. So there are too many such ground states, even if one could calculate in principle such ground states. There are too many of them to keep track of whether a solution is compatible or not. Now, if we once again look at the issue of alternatives, because that will be important later on, once again, we find a situation that is somewhat comparable to the case of inflation and the case of dark matter. There are alternative proposals to quantum gravity that are worked on by smaller groups, substantially smaller groups of scientists than the string community. So those approaches also have been listed already by Karen, some of them. The number of scientists working on those approaches in total may be about 1 order of magnitude smaller than the number of string physicists. Okay, I won't go into any detail about those alternative approaches, but for our epistemic assessment, it will be important to keep this constellation in mind, let's say. At that point, since we had seen this constellation, we see it now for the third time, right? The constellation that there is what one may call a dominant research program, and there are alternative approaches. And the question is, just without looking structurally into the issue yet, we will do that in the third unit, the question is, just in principle, let's say at the level of characterizing a scientific enterprise, what should one make of such a situation? What is the implication of such a situation? And the answer to this is complicated because the response depends on the position one has towards the field and towards the questions that are being discussed. For a scientist working in that field, of course, the ideal situation would be that the scientist does not rely on arguments from authority, because the scientists should view themselves as the authority on the topic. Now, of course, that's ideally, in praxis, this is not fully fulfilled, but it would be the concept of being an acting scientist in the field. Therefore, from the scientist's perspective, the question whether or not a majority of physicists work on a specific subject should not be all that relevant. If the individual scientist, based on the argumentation or based on the reasoning, comes to the conclusion, on my view, this is the most promising approach, that's what they should do, without doubt. And that's, of course, also important. It's also important that the space of possibilities of thinking about the subject matter is exhausted as far as possible by the acting scientists. So that it's important that there is this spectrum of thinking about an issue. There is a problem, of course, in praxis with this approach, because scientists often are expert only on one of the rivaling approaches to a research question. And they enter that position at a fairly early stage in their career often. So one may say they enter that situation at a stage when they are not when they are not in the best situation to judge that selection. And once a scientist focuses on one of those theories, it may be difficult for them to, on their own, judge the merits of the alternative positions. And that clearly is an issue, not just today, but it is an issue in all contexts, scientific contexts, where there is a spectrum of perspectives, and each perspective is fairly difficult to understand. So what then happens is that scientists either aim at being experts enough, so to say, on the alternatives to have a well-founded basis for judging them, or they may rely on testimony of colleagues in their field that actually did look at alternatives more carefully and take this testimony seriously. So this is clearly an element of generating the prevalent understanding in a field about the preferences with respect to various approaches. And it is an aspect that complicates matters, no doubt. Now, if one compares this situation to the situation of a non-expert member of the public, let's say, that non-expert member of the public obviously is at the other end of this spectrum of expertise. And of course, for them, it's a good idea to rely on expert judgment. Now, if there is expert judgment that is split, it may be a good idea to take into account the distribution of expert voices. So let's say if there is a situation where 99% of the specialists say one thing and 1% says something else, it may be the most reasonable perspective for a non-expert to say, okay, I believe the 99% and not the 1%. Because probably the non-expert will not be in a position on their own to judge the independent merits of those two positions. So on that basis, the distribution is relevant for an outsider perspective. And now we come to the philosopher of physics, which is a very tricky question then, because the philosopher of physics is an expert on the subject to some extent, but the philosopher of physics is in most cases not someone who has actively worked on any of the subjects. So they would need to be, they would be ill-advised, let's say, to consider themselves being experts at the same level as the exponents of the field. So they have some level of assessment of those theories, but nevertheless, it seems plausible to say that they should actually take expert advice into account. So they are in a situation kind of in between a little bit, but it seems not to be a good idea to just discard a distribution, let's say a distribution 99% to 1%, and say, well, as a philosopher, I'm objective, I can make up my own mind. That may be less reliable than taking expert opinion into account. And now, what I'm going to say now is my own perspective, my own opinion, even more than anything else I say. But I still want to say it. At least I want to raise the issue, let's say. There is a striking aspect in philosophy of physics to favor minority positions. If you compare the number of papers, for example, to give one example, the number of papers that are based on Mond in physics and the number of papers that are based on lambda CDM in physics, probably, yes, the ratio would be this 99-to-1, maybe a plausible first order assessment, let's say. If you count the philosophy papers on both issues, it's probably fair to say that actually a majority of them looks at Mond. So the question is whether that's a good balance, actually, right? And Mond is not the only example where you can see that there is a very striking tendency there, and there are reasons. There are a number of reasons why this happens. One reason is that the dominant research program normally is pursued by an awful lot of people working on all sorts of details and making the field extremely complicated to understand. So it's an easier task to enter a field as a philosopher of physics where, let's say, 10 people work, and look at those papers and say, okay, so now I've roughly understood what they are doing, while looking into a field where there are tens of thousands of papers, and you need to understand which ones you should know, and so on, and you will never actually fully understand what they are doing. That's one reason. The second reason is that dominant research programs, in a sense, tend to be physically more arrogant, let's put it that way. So they are not as keen and interested to talk to philosophers. So they feel they don't need that, right, in a way. For better or worse, one might say. But that's the situation. While research programs that are fairly small tend to think that they can gain something from getting support from outside the scientific field itself. And the next step, moving outside without moving towards the general public, is to talk to philosophers. So exponents of minority research programs tend to be much friendlier and much more talkative to philosophers. And of course, philosophers are flattered by that. They like that, right? They have physicists who take them seriously. That's another reason. The third reason is a more conceptual reason. In a sense, the most, let's say, the philosophically most interesting reason. And that's the reason that the philosopher tends to argue that to them, all the approaches, as long as they are not empirically conclusively confirmed, are equal. Because they are all options, they are all possibilities. So they all deserve either attention or not. And once they have passed the bar of deserving attention, for them they are the same. All those approaches have raised philosophically interesting questions. None of them has been conclusively confirmed. So the philosophical interest in all of them seems to be the same. So they feel free to choose freely without considering the distribution, which, as I tried to argue before, is not the optimal approach, on my view, towards the matter. It is also interesting to put this current understanding a little bit into perspective, comparing it to the perspective in the philosophy of physics, let's say 30 years ago. And which is roughly, or 25 years ago, which is roughly when I entered the field. So I can tell you what the situation still was, by and large, at that time. At that time, the understanding was that philosophers should not actually look into empirically unconfirmed or inconclusively confirmed theories at all. Because it's not up to them to establish theories. They should philosophize about the theories that have been understood to be viable. So the understanding would be that the scientists first figure out what is the case, so to say, so what the viable theories are, and then they move on, and the philosophers of physics move in, marvel at those grand theories, and try to, or aim at characterizing and assessing them in terms of their philosophical toolset. And this has changed quite considerably in recent decades. And for one reason, it has changed because of the situation we are talking about today, right? It has changed because that increasingly meant that philosophers were confined to discussing theories that were not, that they were, let's say, put it differently, they were barred from discussing most of what physicists at the time were actually doing, because most of the physicists in fundamental physics were actually working on those theories that are not conclusively confirmed yet. So philosophy of physics became kind of less topical in this sense. Yes?
Yes, thank you. I agree completely with you about this at this point. But even an observation about the case of string theory. If you consider this very small community of theoretical physicists that work on quantum gravity, it is true that the most powerful people is working on string theory. But if you consider the global community of physicists, all of them agree that string theory is completely wrong. In other words, what should do?
Yes, so the question is whether, I mean, they are not experts on the theory, so on what basis can they make that judgment? I would also say, I mean, I would say all of them is not quite right, but I would agree that probably today there is a majority of physicists outside the field of high energy physics that has not much trust in string theory. 30 years ago, that was different. What happened, I would say, is that they chose to listen to different experts now than they used to 30 years ago. So they rely, of course, not on their own understanding of the theory, because that is quite limited in most cases. They rely on testimony, actually. And so they decide which testimony they focus on. I would say that's the situation. Yes.
Yeah, I think it's a relevant point. I don't want to use quantum gravity and string theory as an example. Let's say that I have a physicist friend who don't believe in inflation, which is the popular theory, but he is my physicist friend. Therefore, I have more access to talking to him, understanding the view he endorses.
Right.
Should I, then at this point, make a conscious effort trying to give inflation theory more credit because it is the popular view, even though I would say that the testimony of my close friend is someone that I trust, therefore I trust his judgment.
Yes, I mean, generally I would say that, of course, yeah, as a matter of fact, if one knows someone who is an expert in the field and who specifically presents or explains their own specific position, of course that will have considerable impact. Also because that's the most detailed information one gets, simply. And I think the quality of details of the information is of course important from a non-expert perspective, let's say, or a mid between expert and non-expert perspective to make up one's mind. Yes. Yes. So yeah, sure.
So I mean, what you're describing here, I think would be a trustworthy and reasonable way to approach the issue if we lived in an ideal world. But in fact, young physicists have to worry about getting grants. They have to worry about getting jobs. They have to worry about who has political power in the field. And once a research program has achieved a certain critical size, that research program can dominate grant funding and jobs and political power. And most young people aren't going to want to speak up and really push back or question. They're just going to hop on the bandwagon. I mean, I really worry that popularity should not be a good indicator. I mean, think about if we use that criterion in philosophy. We would conclude that analytic metaphysics and analytic epistemology were the most epistemologically robust, approaches to philosophical questions. And philosophy of physics and more formally minded epistemology shouldn't be taken very seriously.
Yes, I mean, I fully, and we will come to that issue briefly. I fully agree that this is not at all a simple situation, and there are those aspects that make the situation even more complicated. I would not follow you on comparing the situation in physics today to the situation in philosophy, and the reason will become clearer, hopefully, in a couple of hours, let's say. because I would emphasize, and I mean to some extent this has already been established by in the previous session. It's not the case that philosophy, that fundamental physics today is decoupled from empirical data. So there is even though a more complex relation to empirical data, there is a relation to empirical data. So if one thinks about the mechanisms that generate trust in those theories, on my view, this is related on connecting to empirical data in a way this does not work in philosophy. So I think the important point eventually to make, and I mean now I just, so to say, I prepare the ground, right? This is not an answer to the problem. It is a perspective that looks plausible, but that at this point still lacks the understanding why do experts think that way about theories, and why do those differences of opinion arise. Yes?
So in social epistemology of science, like it's usually now I think largely accepted, like the deference to a consensus in a simple way is not an epistemically justified stance. Usually, I mean, even in the cases of climate science, which seems to be, which always works at this level of, you know, this percentage of papers has established that there is the connection between the increasing temperature and the CO2. So, like, even there, the social epistemologists, I mean, some climate scientists, or like more philosophical climate scientists have criticized this approach of establishing epistemic credibility or value of a certain theory just by reference to consensus. And they always tend to point towards we need to establish that this consensus was actually achieved through epistemically valuable, reasonable means. And the criteria for that is very, very serious, I think. And I mean, even in the cases, again, of the sciences which are more sort of methodologically traditional, let's say, it's often questioned. And yeah, I mean, it seems to me like, yeah, I mean, maybe we'll say more about it later, but it seems to be very hard to see how you could sort of establish like this sort of epistemic credibility of this consensus in one part of theoretical physics.
Yes, I mean there are two aspects of two parts of the two ways to answer that question, right? The first point to make is that it is one thing to say that consensus or near consensus or a distribution of perspective should be a factor in understanding the situation. It should be an important factor. And another thing to say, it should be the only factor. Now, from the farther you're away from knowledge about the field, the fewer, other aspects are accessible to you. You may look at expertise at various levels, for example. For example, you might, one issue that where philosophy can be relevant is to understand exactly the question you're expressing. So philosophers may understand arguments, for example, bring arguments along the lines Eric was just expressing. And that is an important consideration. And that consideration has to be taken seriously as a philosophical contribution to understanding other influences in generating that consensus, and on that basis, to some extent, questioning it, maybe. And that, from an outsider perspective, those considerations then can play a role, but one needs to keep in mind that they must not play the role of entirely annihilating the implications of distributions of opinion, because if that's the case, what it amounts to saying that actually I have no trust in scientific judgment at all, right? Even if it's 99.9% of the people who are of a certain position, and then there is one guy who says something else, I say I don't know because I don't trust consensus. That's of course not the most promising approach, let's say. So the issue is to find the right balance of the right amount of significance, let's say, of this distribution. But the issue is not whether or not one should take it seriously. That would be my view on this. Yes.
Yeah, so how does philosophy of physics part? So I generally agree with your motivations and what's being raised, but I think there's also a theoretical motivation, which is what's important for exploring these minor approaches. So I don't think that in the case of quantum gravity, philosophers of physics don't usually know which major approaches we have and which are the minor approaches. I think we have a very clear understanding of what are the major approaches.
Sure, of course.
The minor approaches,
Yeah.
because when we want to, one way to examine, for example, the major approaches is to say we have certain assumptions and we get certain part of the theory, certain probability theory. But why do we have these assumptions and not others? If we want to examine this kind of questions, one way to do it is take a minor approach which rejects this kind of assumption, see what happens in the middle, and then with this knowledge we have acquired, then we can actually examine the major approach. So there is this kind of detour, which is theoretical motivation for exploring minor approaches rather than trying to face the major one directly at face value. Because in that case, some of the connections might be obscured, or we end up doing, like, for example, what certain physicists might do, and reasonably so, because they have to actually produce a paper and work and so on. So, like, let's have these assumptions, which may be problematic, but we won't question that. This is what we derive, so. And so in that case, I think that it might be some kind of very weak, probably just very distant contribution from philosophical discussion of this kind of major approaches starting from minor ones.
Yes, I mean, not to be misunderstood. I didn't want to say that philosophers should not look at minority approaches, and the reason you give is one reason for doing so. The question just is, and one should also notice, of course, that in the same way it goes for the physicists that they should decide on their own what they take to be the most interesting research question. That also goes for the philosopher of physics. So at the face of it, it makes sense for the philosopher of physics to think on their own what they take to be the most interesting approach. However, if one observes that a very strong imbalance between research approaches is not at all reflected on the philosophy side, one may ask the question, maybe some considerations here are not sufficiently sensitive to the significance of that distribution. And that's the point I want to make. So it's not the point saying that if someone works on a minority problem, that's not good philosophy. Not at all, of course. These comparing approaches, looking into approaches that are less popular, can be very interesting philosophically, no doubt. But if you look at the overall balance, the question is whether that's the optimal balance for philosophy to have. Of course, this does not suggest a solution because it doesn't take anything from the individual philosophers, let's say, necessary freedom to choose their own research subjects. Yes.
Thank you. I actually agree with you on this. I wonder if you would put this in terms of the fact that theories, let's say, credibility goes beyond, empirical equivalence in the sense that two theories may be empirically equivalent, but one may be more credible than the other, and so that's what maybe some of the philosophers may be missing. Is that one way you would put this?
You mean empirical equivalence with respect to available data, or as a matter of principle? Well, I mean, empirical equivalence with respect to theories that are not fully understood in their implications and their consistency, of course, is a complicated issue, right? So if one criticizes a certain approach, that criticism would be, for example, based on the suggestion either that it is not embeddable within the well-established framework theories, or that it may have an inner inconsistency. And some of those considerations might work well in terms of expressing a situation where there is empirical equivalence on the subject matter, but lack of embeddability, let's say, if you move beyond that. Others, not that much, because they focus on problems of the theory itself as it stands. So it would be one aspect, I think, but it's just one aspect, yes. All right, so summing up, what we have seen in the last 3 hours or so is first that one interesting characteristic of the most influential theories, beyond what has been conclusively established, are theories that are fairly old by now. The fundamental theories are about half a century old. However, they do posit far-reaching new physical structure and have, throughout that half century, one may say, very substantially altered our views of the universe. So they are part of the perspective one has on physics today to a very high degree. And some of them are supported by empirical evidence to some extent, and this is sometimes de-emphasized a little bit in the discussion, but none has found conclusive empirical confirmation. Except for grand unified theories, they have rivals aiming at solving the same or similar problems. In most cases, there is an imbalance between a dominating research program and less popular research programs. In the case of supersymmetry, as we have discussed, this does not apply. This is a more complicated situation. Yes, so that's the let's say, concludes the current status of fundamental physics. Okay, so the topic of this part of the lectures is the sentiment that fundamental physics at this point is in a situation of crisis. So if we start with the canonical view on science, the idea would be, the idea based on emphasizing the significance of empirical data, is that scientific theories make empirical predictions. Those predictions can then be confirmed within a reasonable time frame, and one can on that basis establish the empirical viability of the theory. Now, as long as core predictions of the theory remain empirically unconfirmed, the theory remains a speculation. Now, as we have seen, if we look at the record of predictive success of the theories under consideration here, we have seen that there is some predictive success in case of many of those theories, and to varying degree. If we look at dark matter and dark energy, dark matter in particular is widely considered well established, and this also goes in a slightly more complicated way for dark energy. Well-supported hypothesis due to their agreement with empirical data, even though they are not supported by an actual discovery. Grand unification is, as we have seen, in highly non-trivial agreement with observation. Inflation is viewed that way by its exponents, but this is contradicted by critics of the approach by pointing at the flexibility of model building. Supersymmetry has some quantitative empirical support based on Higgs mass and due to gut, but that's fairly, let's say, not at a very strong level. Low energy supersymmetry, that is. String theory only gets qualitative support from observation, no quantitative support. So there is relevant empirical support, but the situation is much more difficult and convoluted than in core fields of fundamental physics in the 20th century. And of course, it is most complicated in the context of quantum gravity. But there is a wider and general problem for new theorizing, and this can be characterized by the statement that no fundamental theory of the last half century in high energy physics and cosmology has found conclusive empirical confirmation up to now. So those theories are mostly half a century old, but they have not been conclusively confirmed. So in other words, those who initially presented the theory don't work on the theory anymore, most probably, or at the very verge of not working on the theory anymore, and it has not yet been conclusively confirmed or rejected. And there is one core problem to which this is related in various ways, but that is at the center of the issue, and that is the high energy scale where gravity becomes as relevant as nuclear interactions. So the fact that the Planck scale is so far off influences these problems in each of those cases in some way. So if we look at the situation once again step by step, looking at the individual theories, the stories are different in each case, right? If we look at supersymmetry, there were high hopes, as we already discussed, that it would get empirically confirmed at the LHC. And that expectation was mostly based on the naturalness arguments, as we have seen, and solving the naturalness problems would have required a supersymmetry signal at the LHC, which did not happen. The other arguments for supersymmetry, as we saw, do not require supersymmetry to be observable at the LHC. So that's the situation of supersymmetry. Supersymmetry, in principle, could be, if it is a viable theory, could be discovered at the next generation of colliders. But as we also discussed, it is not clear that it would, even if it is a theory that in some way that is conducive or that works as improving gut behavior or works as a dark matter candidate, dark matter particle. In the case of dark matter, as we saw, the situation is that no dark matter particle or object has been observed. And that may also not change in the foreseeable future. Dark matter might be unobservable in the long run. Or some of it might be discoverable at energies close to the ones tested. So it's not clear. If we look at the context of inflation, there is a lot of empirical evidence that is in good agreement with generic inflation models, as we have also discussed. But there is no smoking gun. There was a short period of time, a few months in 2014, when exponents of inflation had high hopes that that was actually happening. And that was when BICEP 2 data seemed to show signatures of primordial gravitational waves, which would have been a strong indicator of inflation. So what this episode shows is that it's not out of question at all that this might happen in principle. 2014 told us what it feels like, so to say, if data pointing in that direction comes along. However, it then turned out that the signal could be reduced to dust effect, so it just didn't happen. It is also interesting to look into the debates on this at the time when it happened. There were conceptual debates on whether that signal is plausible, but I don't want to go into any detail of that. But it is an interesting episode. One problem for inflation is that the options for model building are so vast that even if more specific empirical applies support for inflation was found, this would not single out one inflationary mechanism or one inflationary model. The problem of evidence with respect to gut, proton decay would be an empirical indication of gut. So gut wouldn't be the only possible source for proton decay, but gut in principle predicts proton decay. The question is whether it predicts it at an intensity that can be discovered. It has not been found. Gut particles themselves, so the discovery of the highly massive particles that are added by grand unified theories, they would only show up at the gut scale, which is very close to the Planck scale. So no conceivable experiments could discover them. In the case of string theory, the characteristic signatures of string theory, as just mentioned, extendedness and extra dimensions, are not accessible by currently conceivable experiments based on let's say the canonical understanding of the situation. However, there are considerations, string phenomenology and swampland conjectures, that aim at extracting constraints, and those constraints might improve in the future. So they might improve the picture to some degree, but there is no plausible perspective that they become strong enough to amount to substantial empirical confirmation. So this is the problem of empirical access to the theory. And there is a second important problem for theories of quantum gravity, and that problem is that those theories have not found a complete formulation so far, even after decades of work on them, and they cannot be expected to find one in the foreseeable future. It's not clear what to make of this observation. One might either conclude that it is just so difficult to find a complete formulation of theories of quantum gravity that conventional timelines don't apply, so it may take much, much longer than in conventional context. It might also mean that it is too difficult to ever become feasible. So maybe there is a pragmatic barrier to developing such theories. Or there may be the situation that there just is no complete formulation of such a theory at all. So this would fundamentally shift the understanding of the relation between physics and the world, but it is an option to think about. Okay, so that's the situation, and the situation is very different from what one was used to throughout most of the 20th century with respect to the relation between empirical data and scientific or physical theories. So there are two basic questions here. The first question, faced with this situation, is whether there is something wrong with the way this research is carried out. Whether there is something fundamentally, there is some flaw in the way the science is done at this point. So let's say the background thinking, the analogy, let's say, that would suggest something along those lines would be, let's say, everyday world contexts. So if we think about or imagine a situation where we are in a jungle and we hit an impenetrable and extensive thicket, and we fail to get through for a considerable amount of time, at some stage, actually, it may seem to be a good idea to retreat and look for another passage elsewhere, rather than just carrying on and trying to get through where we are. So the question is whether this way of thinking applies to contemporary fundamental physics. If so, then of course the question is, okay, what does it mean to look for other passages? How would one approach that problem? The basic question, too, is the degree of optimism in the field with respect to the viability of the hypothesis. And in order to assess this sentiment, it is important to keep in mind the distinction we made last time, the distinction between problems to complete a theory and problems and the issue of viability. And I will spell that out a little later, more specifically. So at the face of it, first, if we look at this optimism, this is a quotation from Brian Greene's book about string theory from 1999, so it's an old quote itself. And in this quote, one can feel the optimism at that time. There is nowadays, probably, if one writes a book about string theory, one wouldn't formulate it that way. It's fair to say, however, that there are quite some string physicists who think that way today, but they don't want to be that explicit about it because they don't think that it is conducive to promoting their case. So the quote reads, during the last 30 years of his life, Albert Einstein sought relentlessly for a so-called unified field theory. Einstein never realized his dream, but during the past half-century, physicists of each new generation have been building steadily on the discoveries of their predecessors to piece together an even fuller understanding of how the universe works. And now, physicists believe they have finally found a framework for stitching these insights together into a seamless whole, a single theory that in principle is capable of describing all phenomena. The theory is string theory. So there is a strong commitment, even in the absence of empirical confirmation, that string theory is, at any rate, at the right track. As we saw a few slides ago, on the canonical view, however, string theory should play the role of a mere speculation. However, it does play the role of a well-established theory, and some others of those theories who are not sufficiently or conclusively empirically confirmed do so as well. So they play the role in today's research program that to a considerable extent resembles the role played by a conclusively confirmed theory. And exponents of those theories do have a high degree of trust in their theories, and the question is, why? So that's the second question. So we have two questions. One is the question, okay, maybe something is fundamentally wrong. The second question is, okay, but exponents of those theories seem to think that they are on the right, to have reasons to think that they are on the right track. So how does one balance those 2 points? So this, on the other hand, so this is the green text is an exemplification of the position of an exponent of dominating research program on their theory, despite the fact that there is no conclusive or no empirical confirmation at all. On the other hand, in light of this unusual situation, let's say, unusual situation fundamental physics finds itself in, there has been a highly publicly visible discussion on the current state of fundamental physics that has been going on for at least more than 2 decades now. And a wide range of critical views have been expressed, also expressed in public discourse. Now, it's fair to say that a majority, probably a large majority of the physicists in the field would not be in agreement with those criticisms as they are formulated, but it's fair to say that the overall mood in the field is not overly optimistic at this point. It's not overly optimistic with respect to imminent breakthroughs. Now, what I want to do next is I want to sketch some of those critical considerations. And as you will see, and they are overlapping, I will try to highlight positions that generate a spectrum of critical positions, but even those statements are overlapping. They are overlapping even more than what I present on the slides, because I don't want to be overly repetitive. So the first example, the prime example of criticism of the current state of fundamental physics is Roger Penrose. And he has repeatedly expressed his discomfort with the trajectory of contemporary physics. And he has provided various arguments. One argument he has offered against inflation is a fairly specific one, saying that on his understanding, inflationary theory is unsuccessful because the motivation for inflation is to remove the fine-tuning of initial conditions, but it just replaces it by another fine-tuning with respect to specifying the inflationary potential. I don't want to enter this debate. There are, of course, rejoinders to his position and so on, but just to flag that, so he has specific lines of criticism, and he has a general line of criticism against also the self-confidence of exponents of string theory. And he argues, he makes a very general empiricist point. He argues that without empirical confirmation, we cannot possibly know whether we are on the right track. And there is one very nice quotation in his book, The Road of Reality, that I think very nicely spells out the counterpoint to Brian Greene's perspective. So in a way, Greene and Penrose can be represented as spelling out the paradigmatic views on this, on each side. So what Roger Penrose says is he invites us to imagine a tourist trying to locate a specific building in a vast and completely unfamiliar city. There are no street names, no maps, no indication from the totally overcast sky, as I said, as to which direction, or north, south, or whatever. There is no one around to ask the way. At least the tourists know that the building that is sought has a particular sublime elegance with a supremely beautiful garden. Now, each successive choice of turn is a gamble, and on frequent occasions you may perhaps feel that a different one held more promise than the one actually chosen. If there are too many of those choices, the chance of guessing right each time may become exceedingly small. So therefore, if a theory develops for several decades without empirical guidance, there is not much hope, on his view, that it is still on the right track. A second critical perspective, related of course, would be Lee Smolin's, and Lee Smolin makes a number of additional interesting, offers additional interesting thoughts as to, let's say, why that confidence emerged. First, he argues that string theorists created arbitrary criteria of success that are tailored to being met by the theory. So first they changed success criteria in order to meet them, and then they can point at them and say, look, we have achieved that, and therefore we can have trust in the theory. He also argues that high energy physics is not sufficiently creative and therefore merely continues to follow the same old principles because that's the easiest way to do without empirical guidance. So they still stick to supersymmetry, grand unification, strings, etc. He also argues that exponents of the dominant theories are uncritical due to groupthink. And this has been mentioned already. So the mechanism is that there is a high prestige group and highly influential leaders and strong incentives to be accepted within the group. For example, because if you're part of the group and you submit a research program along the lines that is favored by the group, you have chances to get the money. And you have also better chances to get positions. One needs to add that this is also a statement 20 years ago when the dominance or the popularity of string theory was much higher than today. Nowadays, it is not that easy to get money for string theory, and it's not that easy to get positions for string theory. So this situation clearly has changed, but 20 years ago that was the case. So, in light of all or due to all these mechanisms, the dominant theories, in particular string theory, attracts an undue share of money and scientists. And the reasoning is just not, to that end, is just not justified. A third criticism, once again related, but with a slightly different emphasis, is put forward by Ellis and Silk. And they argue, with focus on the discussion on inflation and the multiverse, which they are most interested in, that it is important, or it would be important, to defend the canonical paradigm of empirical theory confirmation against tendencies to have undue trust in theories without substantial empirical confirmation. So they, along similar lines as Penrose, aim at defending the empiricist paradigm of theory confirmation. They argue that compromising that canonical paradigm would invite the risk of making the criteria of theory acceptance arbitrary, and therefore it would threaten the core of the scientific process. So yes, so this, of course, this position has parts of both Penrose and Smolin in it. A fourth, slightly different perspective on the issue has been presented by Sabine Hossenfelder. Sabine Hossenfelder suggested that physicists stick to the unfruitful paradigm that lies behind much of high-energy physics, such as string theory, supersymmetry, grand unification, or also inflation, which is also a theoretical approach, due to an ill-advised preference for beautiful and elegant theories. So the idea is that fundamental physicists have these unfounded ideas that physical theories must be beautiful, and therefore they try to find beautiful answers to their questions. And that has led them into the situation they find themselves in today. Carlo Rovelli is also a pronounced critic of the current state of fundamental physics. Like Lee Smolin, he is a main exponent of a rivaling approach to quantum gravity. Rovelli claims that, and I just focus now on a more recent statement of his. You can find several statements that would also align with what has been said up to this point. Rovelli claims that a misguided focus on falsificationism brings scientists to expect that the theory they are dealing with today will be falsified at the next step of empirical testing. So he argues that, for example, supersymmetry is so popular because scientists are in the habit of expecting that when they make a new experiment, the old theory will get falsified. So they have a crude and inadequate understanding of what Popper says, and therefore they think that way. And this way of thinking, he argues, gives unfounded boosts to beyond the standard model theories, such as supersymmetry and grand unification. And that boost is based on the fact that those theories imply additional physical phenomena that would be at variance with the current theories. So they would offer a basis for those theories being rejected. Yes?
Sorry, I actually have a question about the last slide. So
Yeah.
there is some theory that is natural but not beautiful. Like I have a hard time understanding the difference between naturalness and beautiful theory.
Naturalness on her understanding is one good case of beauty. So she argues that theories that are not natural are not considered beautiful, and therefore they are taken to be in need of replacement or of further amendment, let's say. But of course, it's not the only, naturalness is not the only criterion for beauty. So in her understanding, for example, the concept of the symmetry structure, for example, is beautiful. So physicists focus on symmetry structure because they find that beautiful. She does not offer a very specific definition of what beauty is, and she doesn't feel obliged to do so because she says that's what the physicists say, right? It's not her task to establish that there is a consistent concept of beauty even. But she suggests that actually we will come in a few slides. We will come back to that. I will have to say a few words about her criticism.
Maybe you'll come back to it, so you don't have to answer it to me. I just right, because simpleness, we do strive for a simple theory. It's a simple theory, a beautiful theory, or right. So what particular part of the beautifulness that she thinks we should try?
Yes, I mean she would argue that simplicity also is a sign of beauty. So all overly complicated theories are not beautiful on that account. Yes.
Yes, about the Rovelli point of view. In the other, okay, it seems to me that there is a bit of difference in his point of view. His point of view is that the wrong part of falsificationism is the fact that you can invent what you want, a lot of fantasy. The important point is that it is possible to falsify. And Rovelli is saying that it is not a good idea because when you make science, you should stay very near to what already happened, and so do not give so much importance to fantasy. Okay, it seems a bit.
Yes, I would say, I mean, if I read him correctly, I would say that there are both aspects in his criticism. It's right that initially his criticism was more focused on the speculative character of theories that are far beyond any empirical accessibility. There is a recent Science article where he more focuses on the other end of the spectrum, and presumably that has to do with the fact that, of course, this kind of criticism does not apply to low-energy supersymmetry. But the failure of the discovery of low-energy supersymmetry is an important aspect of that feeling or sentiment of crisis in physics now, because there was a very clear expectation that low-energy supersymmetry would be found. So that was not about a theory that is off at the Planck scale. It is a theory that was expected to be right around the corner. And so Rovelli's explanation why people were so confident about that is that they adhere to an inadequate understanding of Popperian falsificationism, where the fact that a theory must be falsifiable is confused with the suggestion that actually theories probably will be falsified around the next corner. That's what he spells out in this recent article. And I focus on this element of criticism because I think it's a new aspect, a new suggestion, let's say. Yes, and these are not the only views that have been presented. There is further discussions by physicists like Daniele, by philosophers, by mathematicians, Peter Voigt, and by several science journalists who wrote highly critical books about the current state of fundamental physics. There is also a specific criticism that that has a more specific focus, but kind of blends in with the overall suggestion that there is an over-exaggerated confidence in theory building nowadays. One criticism of that kind is the one by E.S. Loeb and Steinhardt, the criticism of the theory of inflation. And what E.S. Loeb and Steinhardt argue is that trust in inflation is unjustified because of the high flexibility. I mean, that's a very boiled down characterization of what they say, but just to sketch the thrust of the reasoning. It is unjustified in light of the extreme flexibility of inflationary model building. So on that basis, they argue there is no way of establishing individual models and no way of, therefore, of establishing or testing the theory of inflation either. So if the theory is overly flexible, it becomes untestable, in effect. That's what they say. So there cannot be a basis on their account for trust in the theory in light of agreement with data. Criticism that is kind of slightly goes in a similar direction has been expressed by David Merritt, an exponent of Mond, who has criticized the wide consensus in favor of dark matter as scientifically unjustified, because first, he argues that there is this, as we discussed already, there is this successful prediction of a rivaling research program, Mond, the prediction of flatness of galaxy rotation curves. And second, they also argue that the theory of dark matter is so flexible that it is not falsifiable. So it is not scientific even, they would argue, or he would argue. So there is this broad spectrum of criticism. One should also, to make the picture even more complicated, one should also emphasize that there are, coming from individual researchers, patterns of criticism of endorsement that are not based on a general skepticism with respect to confidence in empirically unconfirmed theory, but that they, for methodological reasons, focus on criticizing confidence in a specific theory. And a good example of that would be Robert Brandenberger, who is a strong supporter of high credence in string theory, but he sees no good reasons to have credence in inflation. So he thinks that the argument, the line of reasoning in the absence of conclusive empirical confirmation that is taken to support the theory in inflation is misguided for specific reasons that he would explain in detail. So in this case, this is a discussion going on specifically about credence in a theory, but it cannot be viewed as an expression of general criticism of credence in empirically unconfirmed theorizing. So there are various different views on this, a very broad spectrum of views, which of course makes the situation even more complicated. So I want to raise in the last minutes of this lecture some general issues of the of some of the universal lines of criticism, and then continue to point at the very serious issue that is nevertheless addressed by those lines of criticism. So I would point out that some of the described criticism is based on underrating the genuine empirical support for several of those theories. So I have emphasized this empirical support yesterday in a number of cases, and it is important to understand that there, even if one talks about proper empirical confirmation, so agreement between a theory's implication and data, there is a wide range of degrees of confirmation. And if one acknowledges that, one sees that several of those theories under discussion here are to some extent empirically confirmed. Dark matter clearly is, grand unification clearly is, supersymmetry is to some extent, low energy supersymmetry that is to a lower extent, and maybe inflation is, right? In inflation there is this conceptual discussion whether that's the case or not, but the case can be made that inflation has quite considerable empirical confirmation. So these are not cases where one needs to say, okay, they just deal with speculation, even on a genuinely empiricist account. Even an empiricist can acknowledge that this is not a case of speculation anymore. This is a case where there is empirical confirmation, but it's not conclusive, or maybe not even close to being conclusive at this point. Second, and this comes back to Sabine Hossenfelder's point, it seems inadequate to say that physicists follow elegance in an unreflected way. And interestingly, I think the nicest place to look for that, to understand that, is her book, which is a really nice book, actually. It's a very well-written book. And a large part of the book is a report of her interviews of physicists. And if one reads these interviews without framing them the way she does, so if one just takes them and reads them in isolation, let's say, one notices that they are highly reflective on the concept of elegance and on the way in which they take themselves to take elegance into account. I won't go, I don't have the time to go through those examples. It's actually, if one has the prejudice that physicists are not overly reflective on what they are doing, it is actually surprising, if one has that prejudice, it would be surprising, let's say, how reflective those responses are. They're excellent responses, really interesting responses. And in a nutshell, what they say is that they don't have a naive concept of beauty that they follow at all. They have other guiding principles that one might frame in terms of beauty, but they are much more closely rooted in a rational understanding of why they are pursuing one avenue of research rather than another. That would be their first point, and they make that point in various ways. And the second point is they point out that it's not at all true that the concepts that are dominant right now were initially, when they were proposed, considered elegant or beautiful. And this goes for quite a number of those concepts. For example, extra dimensions were initially considered appalling and ugly, and actually a reason for dropping the theory. Abundance of particles in several contexts was considered not at all beautiful, but something that would suggest dropping this approach. The landscape of string ground states would be another case. The multiverse would be a case. Anthropic reasoning would be a case, if I had the spelling right. So those were concepts that were initially not considered simple or elegant at all. But they gained traction for conceptual reasons. They gained traction because within the framework of thinking about this, they seemed inescapable. So they were established for that reason rather than for reasons of beauty. Yes, and finally, I don't know, should we close now or should?
We can maybe have a couple of questions.
Yes, and then we continue in the afternoon.
Are there any questions? So,
You mentioned earlier this conventional timeline, I think you put it. And,
Mhm.
I'm curious about why we expect this progress to be faster than it is. There's like, we had Aristotle for almost 2,000 years, and then Newton for a couple of hundred, and then there's a flurry of like unprecedented activity with a lot of like achievements, and now it's much more still. But it seems like we're looking at this outlier really, and like basing our expectations on that. So what is the conventional timeline grounded in?
Yes, that's a good question. As you say, one might argue that the phases of scientific research and physics in particular differed from stage to stage up to this point, and this now is another stage. And there were cases, as you say, where one dominant theory was not considered up to change for several hundred years. However, on the other hand, one can say this was a highly fruitful framework for more specific theorizing. And this theory found confirmation, empirical confirmation in a variety of new contexts throughout that time period. So one might rather compare that to the period of confirmation of the standard model rather than to the current situation where there is no prospect of confirming anything, so to say. So if there is a very successful theory, and that theory still is in the business of making interesting new predictions, and then you can test that predictions, there is progressiveness, at any rate at the level of experimentation, and maybe also at the level of theorizing in more specific contexts devoted to adapting to the data one then finds. And this, so it's still different from much of previous physics, it's fair to say. But yes, of course, yes, one may say the characteristics of scientific progress has changed before, and now they are different once again. That's the story, so one should be less surprised about this. I agree. Yes.
One last question. No further question? Okay.
May I say something This wonderful book by Leonard Susskind. It is wonderful book by Leonard Susskind about black hole war. There is also a biographical part, and at a certain point, Susskind went at Columbia speaking with Feynman in the 70s, saying that he's interested in quantum gravity, and Feynman said, no, it is not good. Before 500 years, we have no kind of evidence about this topic. It's better that you leave. So the point is, possibly it is not so epistemologically correct to work on this program. So it's not only the fact that you find all road not so easy to pursue, but also that possibly it is not so clear. Okay.
Yes, I mean, of course, they are. Let's say there are all sorts of general expressions of regarding the development of fundamental physics from famous physicists, and they are notoriously inconsistent with each other. Let's say. Another point to the point Feynman makes is that. At the time when he made that statement, which was probably in the mid-60s, right? At that point, what he was pointing at is that at that time there was a highly progressive and interesting, empirically driven part of fundamental physics, which is the development of the standard model of physics and the full understanding of the standard model of physics. So Feynman on this can be read in the way that given this situation, there are so relevant things to be done close to what is testable. Why do you want to look into something where it's not clear whether it's testable in the foreseeable future at all? So this, of course, would be a situation quite different from the current situation. Yes.